Hi, I'm Curtis, and I'm going to be talking about our work on resolving Lamb's problem by generating a collection of unsatisfiability proofs using a SAT solver. Now, Lamb's problem comes from a branch of mathematics known as projective geometry, and this was a very famous problem because it was open for hundreds of years and was resolved finally using a massive supercomputer search. They actually got a lot of press when this was solved in the late 1980s, for example, appearing on in the New York Times. Now, I want to talk about how we were able to go about resolving Lamb's problem using a SAT solver. But first, what does SAT mean? SAT is just short for satisfiability. This is a classic problem from logic where you're given a logical expression and you're asked, can you make this expression true? Is there some way to assign values to the variables which makes the whole formula true? We'll just focus on the Boolean domain, so the variables are just true and false. Now, in theory, this makes the problem easy because you could just try every possible assignment to the variables. There's too many in practice, though. But what is very surprising is that SAT solvers, which are programs which have been designed to do solving the SAT problem, they're actually very effective in practice on many cases. In fact, and this is mind-boggling, but there are people who, like hardware and software engineers, who will actually translate their problems into logic just to be able to run a SAT solver on their problem, because SAT solvers are actually the fastest known way of solving a problem which has nothing to do with logic. So it's very strange. Another example where this happens is in discrete optimization. So as an example, take a look at this chessboard. I put a queen on every square, and I'm going to ask, okay, how many colors are necessary if you want to color every queen, but the queens which could attack each other must be colored differently. So any queen which is in the same row, column, or diagonal must be colored in different colors. It turns out that you need at least 9 colors to do this. There's no 8 coloring. And so how would you go about showing or proving to someone that there's no 8 coloring? You could give them the 9 coloring. This is found very quickly by a SAT solver, but the SAT solver actually does something more interesting. It provides you with a non-existent certificate that there's no 8 coloring, so that a third party doesn't actually have to trust your word for it. They can just check the certificate. And this is the property of SAT solvers we'll be using in our work. The other type of software we use is known as a CAS, or computer algebra system. And these are software which is designed to do mathematics at a very high level. You can give them mathematical objects like matrices or graphs or groups, and then ask to do computations with those objects. Here's a graph that you could ask, okay, what's the symmetries in this graph? And then do computations in that automorphism group. This brings me to the SAT plus CAS paradigm. SAT solvers are really good at doing search. The SAT problem is inherently a search problem. The CAS are really good at doing mathematics. However, SAT solvers are not so great at doing math, they're not very expressive, and CAS are not so good at doing general purpose search. But there's lots of problems where you want the best of both worlds, right? You want, in a problem like Lamb's problem, we really want expressive mathematics, but we also want really efficient search. And so SAT plus CAS is a perfect fit for such a problem. In my research program the last couple of years, I've been developing systems that have an interplay between SAT solvers and CAS. For example, this matrix here was actually found using MathCheck, which is the software we've designed. You can check the website. This is actually a cross-stitch of a Hadbar matrix. So this is, my partner does cross-stitching, and she put this together. The stitches represent ones, and the lack of a stitch represents a -1. And then Hadbar matrix means any 2 rows are orthogonal. So it's very hard to find such matrices, but we were actually able to find perform searches for larger matrices than could have been searched before because of the power of the SAT solver when combined with the CAS. So we've looked for lots of different things in number theory and graph theory, and now what I want to talk about is projective geometry. I love projective geometry because it has a really nice history. It goes back all the way to Euclid in 300 BC. Euclid was a mathematician who did something interesting. He was the inventor of geometry. Well, at least the axioms for geometry. So Euclid defined a couple nice simple axioms. He said they characterized all geometric principles. The interesting thing was, one of his axioms kind of stood out. It was more complicated than all the others. This bothered some mathematicians. They thought, okay, let's prove this more complicated axiom in terms of the simpler axioms. Natural thing to do. They tried to do it for 2,000 years and failed. Consistently and repeatedly failed. It was eventually realized in the 1800s that it was a wild goose chase. It was impossible. The reason it was impossible is because there are alternative models of geometry where this parallel postulate will fail, because parallel lines won't even exist, which is very counterintuitive. But in fact, in a projective geometry, all lines are going to meet somewhere. You can replace Euclid's parallel postulate with a projective axiom saying any parallel lines are going to meet at a unique point. Once you know that these things exist, you could go about trying to classify them. Mathematicians have done this. In fact, they've succeeded in all the finite cases except for one very interesting case. So if the dimension is 1 or 3 or greater, they've solved the case. But exactly 2 dimensions is, to this day, still open. We do not know all the projective geometries in dimension 2. These are known as the projective planes. They satisfy a couple of very simple, elegant axioms shown here. And I can demonstrate for you some simple examples. Here's a triangle. It actually is a projective plane of order 1. It just says that any 2 lines are going to define a unique point. That's a vertex here. Any 2 points are going to define a unique line, one of the sides. And the same number of points lie on every line. It's going to be, in this case, 2 points in every line. It's going to be 1 greater than the order. So the question is, can we go to, say, order 2? Indeed, we can. And here's a visual representation. Now, some of you might be thinking, okay, you totally cheated here. You're pulling our leg. You cannot draw a line like that, right? This looks like a circle. This is not a line. Well, and I can draw it however I want, because as long as I satisfy the axioms, I'm fine, right? You can verify for yourself that this is a line. This circle is a line by the definition that I have on the slide here, right? Check that it satisfies each of these properties. Now, we can actually go even one step farther. This is a projective plane of order 3. And it gets a little messy to draw. There's lots of colors you need to use and so on. However, you might now conjecture you could always do this, right? Or maybe it tops out at some point. The truth is, you can go up to 9. Projective planes of order 9 and exist in all smaller orders except for 6. What happens at 6? This is very interesting. In fact, it's a case you can just rule out. There's an obstruction which totally removes it. You don't actually have to draw all the points on a piece of paper. There'd be 43 points in this case. It'd be a mess. Now, what about order 10 case? This is a very interesting case because nobody knows any projective plane of order 10, and yet nobody knows any theoretical obstruction why one shouldn't exist. So it'd be natural to conjecture either way. Maybe it exists, we just haven't found it. Maybe it doesn't exist and we just don't know any obstruction of why it doesn't exist. Now, this problem became known as Lamb's problem after Clement Lamb extensively studied this problem for basically a decade in the 1980s. And in fact, as I mentioned, he was able to resolve it using a computer. This was already a famous problem, though. Even in the 50s, Hall here was mentioning or raising the possibility maybe computers could be used, right? Because lacking a proof either way, if mathematicians can't decide the problem, maybe computer scientists can by running a search. Now, how would we actually go about running this search? You can use what's known as a representation known as Incidence Matrix. The idea is you have the lines of your plane are going to be represented by rows of this matrix, and the points of the plane will be represented by columns of this matrix. And you have a 1 in the ijth entry if the ith line contains the jth point, right? So every row here is going to contain the same number of 1s, and then the projective axiom is going to say that the inner product of any 2 rows is exactly 1, corresponding to any 2 points have a unique intersection point. Now, you could, in theory, try to run a search for these matrices, but there's way too many of them. You're never going to search them all. It's a non-starter. But mathematicians have some very, studied these structures extensively and have some very nice properties about them from coding theory. The idea is we have 2 quick definitions here. First, the code associated with a 0-1 matrix is just the row space mod 2. It's just a set of 0-1 vectors. Take the linear span. The code, or the weight of a 0, 1 vector is the number of ones in the vector. All right, so it's also known as the Hamming weight. The reason I give these two definitions is because of the following breakthrough from Asmus in 1970. He did something interesting. He assumed that the projective plane of order 10 exists. We don't know if it does, but he assumed it and then derived properties that the code must satisfy. Very curious, but in fact, you can derive properties about which code words of which weight must exist. In fact, there must exist, if the code exists, there must exist vectors of weights 15, 16, or 19. This dramatically limits the search space. In fact, it basically splits it up into 3 cases. Each one can be solved in sequence. And in fact, this was done by a team of researchers shown on the slide here, culminating in LAM search on a supercomputer in 1989. You can see the running times significantly increasing as the weights increase. Now, but at the end of the day, they did not find any code words of 15, 16, or 19, and therefore, by Asmus's result, is a proof that projective plane of order 10 doesn't exist. Or is it? Because this is not a proof in the mathematical sense of proof. This is an experimental result because the authors were upfront about what they did. They wrote custom written software that was run a single time on a single piece of hardware, and at the end of the day, there was no certificates produced. You just have to trust the computer, right? When the computer says, okay, search is complete, nothing found, how do you know, right? Maybe there was a glitch. There was either a bug or an administrative error or a hardware error. You just have to trust the computer. And so one of the impetuses for our work was to put things on a more sound foundation and do a check for discrepancies. And in fact, we did not find a discrepancy with the final result, but we did find discrepancies not only with the original search, but a verification of the search about a decade ago. So the verification found discrepancies, and then we found discrepancies on top of the discrepancies. This just goes to show how difficult it is to write custom written software, right? Almost all software has bugs. This brings us to non-existent certificates, because if you can generate certificates like this, you don't have to trust any search. The catch is you have to be able to use a SAT solver to do this, right? As I mentioned, SAT solvers can generate these certificates, but they rely on some encoding into Boolean logic. Boolean logic is very primitive. You only have every variable has to be either 0 or 1. This is actually nice from an incidence matrix perspective, because incidence matrices have exactly 2 values in each, for 0 and 1 for every entry, right? So we let the 1s be represented by trues and the 0s be represented by false. Now, how would we go about encoding the projective axiom, right? We just have a variable for every entry in our matrix, but to say the inner product is exactly 1, we can split this condition up into 2 cases here, right? You want to split it up into the most primitive form. First, every pair of line must meet up most once, and then every pair of line must meet at least once. This will then say every pair of lines meet exactly once. Let me go through each of these in turn. So here's an example. What you can do is actually fix some entries in advance using some of the mathematical properties. So the 0s here are to be denoted by whites, and the 1s are being denoted by blacks. The gray entries are unknown. These are the entries that the SAT solver would have to determine. And take a look at these two rows, right? These 2 lines. If we want to say that the lines meet at most once, then those 2 highlighted entries cannot both be true. If they were both true, then the lines would meet at least twice in contradiction. So what you can do is encode it as a logical clause shown at the bottom here. This is logician's notation. It's just saying not A or not B. At least one has to be false. This is just one clause. There's lots of clauses which look like this, and I'm just giving you one example. But now let's look at the same 2 lines, and now let's encode lines must meet at least once. This time, take a look at these 6 highlighted entries. Now, at least one of these entries has to be true, because if they were all false, the lines would not meet at all. By inspection, you could see their inner product is 0. This gives us another clause saying A or B or C or D or E or F, at least one of these has to be true. Again, there's lots of clauses which look like this. This brings me to the CAS. So the CAS is useful for performing what's known as isomorphism blocking. The way it works at a high level is like this. The SAT solver, the search is enormous, and the SAT solver is constantly finding partial solutions to this incidence matrix. Here it would be an example. It's a 6-align 4-point partial projective plane. So let's say we give it to the CAS. We say, okay, here's a partial solution. The CAS analyzes it and says, oh, well, wait a minute. If I rotate this 180 degrees, I get something which is, it looks the same, right? It's isomorphic or symmetric. Therefore, we can block it because by the simple reasoning that anything which is derivable or extendable from the first is also going to be extendable from the second. So any solution that could be found from the first will also be found from the second. So we can just block the second. We're not losing anything up to isomorphism. So this dramatically reduces the amount of search as necessary because every time you find a new symmetry, you limit the search space. And in some cases, there is huge numbers of symmetries. So in each of the possible code words weights, 15, 16, 19, we actually generated non-existent certificates for each and then verified them with a proof verifier. You can see here the amount of computation and the size of the certificates. And not only were we the first search to actually verify using certificates, we were also the fastest known search, and in some cases by a huge margin. So for example, in 2011, the verification required 16,000 hours to solve the weight 16 case, and we did it in 30 hours, right? Because we were able to exploit a huge number of symmetries that happens to exist in that case. So you can just see the power of the CAS. It would not be possible in any reasonable amount of time without using that CAS. So this is not to say this is the end of the line. There are still a couple of necessary places where you have to trust. First of all, you need to trust the SAT encoding, right? It's pretty simple, but you also have to trust the script to generate the SAT encoding. This is relatively easy to write. At least it's easier than writing, say, search code. You also have to trust the proof verifier. This is pretty standard because these are well-tested pieces of software. They're thought to be pretty rigorous and bug-free. And the third case is you also have to trust the isomorphism blocking clauses. We used a CAS known as Naughty. This is a library that it's well written, but it's probably the most complicated software that we relied on. However, whenever Naughty said that two things were isomorphic to each other, we were able to explicitly verify that isomorphism. So that gives us some assurance that Naughty actually was performing things correctly. So I really just want to stress, in conclusion, how many different types of problems this is applicable to. Yes, LAMMPS problem is a great case study, but whenever you have a problem where you need fast, verifiable, and expressive searches, SAT plus CAS is a great way to go. The SAT solver gives you fast and verifiable, the CAS gives you expressiveness. Now, yes, you might have to think about your problem in different ways. Both SAT and CAS are kind of niche areas of computer science. But this is a budding field, right? There's starting to be interplay between them because people are starting to realize the power that you can get by combining these two systems. And the big upshot is you avoid writing special purpose search code, right? Speaking from experience, I know that this is code which is very hard to write, hard to make efficient, and almost impossible to verify. Whereas if you're using a SAT solver to perform your search, SAT encodings are relatively easy to write. SAT solvers are already very efficient. There's decades of work gone to making them efficient, so why not take advantage of that work, right? Rather than trying to write your own efficient search. Plus, the SAT solver at the end of the day, you don't even have to trust it because it provides you a certificate which can be verified. So we're really excited to push this to new applications and new paradigms and new domains. And so I'm looking for students, I'm looking for new collaborators, and we really want to just see how far we can push this. As I mentioned, this is a budding field of computer science. There's an SC squared workshop, which is being run yearly for the last 5 years. So if you're interested, get in touch. My website's here. So I'd be really appreciative if you pass on my contact info to anyone you think might be interested in pushing this paradigm forward. And I'd be very happy to take any questions at AAAI. So thank you so much, and I'll see you in the new year.